Welcome to Lecture 43 in this series of modules on statistical quality assurance and statistical process improvement. We begun discussion of design and analysis of experiments, initially considering what can be done if one simply treats the set of experimental conditions as if they are just some list, some unstructured list from 1 to R of such sets of experimental conditions. In this module, we're going to begin to take account of the fact that experiments are done with factors, and in particular talk about data sets that have two-way structure, so-called two-way factorial structures. So here's the basic set of assumptions we're going to operate under. We're going to suppose that some factor A has some number of possible levels, is the jargon to say the number of settings of factor A. Factor B has some number of levels J, and that data are collected for every combination of a level of factor A and a level of factor B. That results in data that can be thought of as laid out in a two-way table. If we were going to invent some kind of notation for that, we might say that the response at level I of factor A, level J of factor B, the kth one of those will triple subscript as yijk. In the way we're going to think of this thing as laid out, I is going to index row and J is going to index column. So factor A has possibility for its levels of 1, 2 up to I. Factor B has levels 1, 2 up to J. That makes a table that has I rows and J columns, I times J cells, and in any one of those cells we can think of there being data collected. So in the first row and the first column there are data values that are Y11s with the third index saying which data point is under discussion. In this cell, we're in the first row and the second column, so there'll be Y's with the first index saying row 1, the second index saying column 2, and then the third index saying we have data values 1, 2 up to some number for the first row and the first column. We're going to assume that this data layout is complete in the sense that one has data in every cell. This two-way table structure is typically called a factorial structure. And the name of this section, the name of this module, to say that we're going to talk about two-way factorial studies, is to say that we're going to think about data that have this kind of two-way table structure, and we might talk about an I by J factorial, saying there are I rows and J columns, and we're going to say that it's complete, meaning that there are data in every possible combination of a level of factor A and a level of factor B. The Glass-phosphor study that was looked at in modules 41 and 42, there are two glasses, glass 1 and glass 2. There are 3 phosphors, 1, 2, and 3. That example, we treated it originally as if there were 6 different ways to make television tubes, but those 6 different ways to make television tubes organize themselves naturally into 2 rows and 3 columns. Here, what I've recorded are sample averages for each of those ways of making television tubes and sample variances for the data that were associated with those 6 different setups. I've also added averages of row averages, and the kind of notation that gets used is to say for row 1 we'll talk about a y bar 1 dot, the dot saying average across these 3 values. Y bar 2 dot, we average y bar 2 1, 2 2, and 2 3 to get y bar 2 dot. We could average down columns to get these values, and then average either these guys or those guys to get an average of the row averages or an average of the column averages. These averages are, we're going to think of them as we're going to calculate them as unweighted averages. So regardless of what the various sample sizes are in these cells, y bar 1 dot is the first cell average plus this average plus that average divided by 3. Y bar dot 1 is going to be cell average in this cell plus cell average in that cell over 2. Here's a useful way to plot data from a two-way factorial study. This is a so-called interaction plot. What one does is put on the horizontal axis one of the factors. It's natural in this particular example to say put phosphor, which was on columns having levels phosphor 1, 2, and 3, and then put y on this axis. I've plotted the data values here for each of those 6 conditions using different symbols for glass number 1 and glass number 2, and then have added these line segments connecting y bars, connecting sample means. And that little picture actually tells pretty much what's going on in this data set. As one looks at that picture, one notices a big difference between glass number 1 and glass number 2, notices somewhat smaller differences between the phosphors as one goes left to right, and notices that the picture here for glass number 1 is very much like the picture for glass number 2, just simply moved up some. That there's a fair amount of parallelism between those two traces that I've drawn there. A better interaction plot is made using not just plotting the data, but rather plotting the y bars with confidence limits set about them. So I've used here 95% confidence limits for the tube type means that were calculated in module 42. That means I've taken y bars and added plus or minus 10.44 microamp current error bars around them. And so that gives us some idea as to whether the difference that we seem to be seeing between glass 1 and phosphor 1 is something that's likely to be reproducible, or whether that's just somehow an artifact of a very noisy data set. In this particular case, the fact that those error bars are very much swamped by the size of this difference between glass 1 and glass 2, looks like we could say qualitatively that glass has a detectable effect. The factor glass is important Phosphor, it's not so clear. We're going to end up deciding that it is detectable, but it's substantially less detectable than is the difference between glasses, the effect of the glass on current requirements. So here is just a recapitulation of what I've just said, looking at those two interaction plots. In the next module, we're going to come and make these things, begin to make these things more precise in terms of talking about defining effects quantitatively and making estimates of them, making confidence limits from them or for them.